Hello everyone, welcome back to Advent of Code 2025. We're moving on to day 11 today. As you can see here, I didn't end up finishing part 2 of day 10 yesterday. I had a couple of approaches, and I mean, obviously this is all covered in the video, but it was a very long video. You could be excused for missing some of it. I had one approach that was correct, but far too slow. And then I had another idea, and I tried shelling out to 2 different libraries to help me implement this idea rather than doing a bunch of drudge work. Well, I guess I only tried shelling out to one. Then I concluded, okay, there's another one I could work with, but it would be too much work, so I didn't. So, no perfect this year. Maybe I'll revisit, because it would be interesting to revisit, like, using Z3 from Haskell, but I didn't want to do it, like, right now. So, let's move on to day 11. Reactor. You hear some loud beeping coming from a hatch in the floor of the factory, so you decide to check it out. Inside, you find several large electrical conduits and a ladder. Climbing down the ladder, you discover the source of the beeping. A large toroidal reactor which powers the factory above. Some elves here are hurriedly running between the reactor and a nearby server rack, apparently trying to fix something. One of the elves notices you and rushes over. It's a good thing you're here. We just installed a new server rack, but we aren't having any luck getting the reactor to communicate with it. You glance around the room and see a tangle of cables and devices running from the server rack to the reactor. She rushes off, returning a moment later with a list of the devices and their outputs, your puzzle input. For example, so we have like a key linking to multiple values, it looks like. Each line gives the name of a device, followed by a list of the devices to which its outputs are attached. So BBDDEE means the device BB has 2 outputs, one leading to D and the other leading to E. The elves are pretty sure that the issue isn't due to any specific device, but rather that the issue is triggered by data following some specific path through the devices. Data only ever flows from a device through its outputs. It can't flow backwards. After dividing up the work, the elves would like you to focus on the devices starting with the one next to you. An elf hastily attaches a label which just says you, attaching it to me, presumably. Or maybe to the device that's next to me, I guess. I don't know. Either way. And ending with the main output of the reactor, which is the one device with the label out. To help the elves figure out which paths are causing the issue, they need you to find every path from you to out. So how many different paths are there from you to out? So presumably there are no loops, or there would be an infinite number of paths. And at least for part 1, this seems pretty straightforward. It feels like there's a problem like this in Advent of Code every year, where they ask you, like, here's a thing that looks like a tree, but actually it's a graph with, it's an acyclic graph where, like, you know, there are many paths from the root to one node. And usually they have these, like, have a surprisingly high redundancy count, so that if you just kind of naively said, oh, I'll do a breadth first search or whatever, I'll just traverse the entire tree from you down to out every way I could and count the paths, you run into problems. But this kind of problem is actually perfect for exhibiting a cute Haskell trick that makes this whole thing quite easy, where you can do what's called tying the knot, building rather than a recursive function, well, I was going to say a recursive data structure, but of course those are quite normal. A tree is a recursive data structure, right? A tree is composed of nodes, and what's a node made out of? A node. But what I mean in this case is, like, a data structure that contains within it links back to itself. Like, you know, a tree where you can build an infinite tree, for example, if a node's, you know, right branch goes to out, and its left branch just goes back to the node itself. These are sort of easy to build in imperative languages if you want, by constructing a node, then constructing its child, then modifying the child's parent pointer to be the node or something, right? In a functional language, it seems like that should be impossible, because how do you create a node that links to itself if itself doesn't exist when it's created? But in Haskell, with laziness, you can actually do this no problem. And so so you can end up building these infinite recursive data structures. Now that's not exactly super helpful here, because we don't need a self-recursive data structure exactly. We aren't going to have a tree with loops in it. We could build one, but that's not the point. Another thing you can do with the same technique is build a data structure that refers to itself in a lot of complicated ways, where it might be hard for you by hand to work out the order of dependencies. Like, in order to compute the answer to I need to know what's in out. And okay, then, well, that means I can't compute HHH, so I know I, but I also need to know FFF before that, before I can know HHH, right? And so, like, there's this kind of, all right, you could do a topological sort of these and resolve the ones at the bottom level first and trace those up to their parents and resolve those. But it's like a lot of work. And you can convince the Haskell runtime to do all of this analysis for you. If you just build a single, no recursion at all, just a flat map where the key is AAA and the value is how many paths there are to out, just a number. The trick is that in order to compute the value for AAA, wait, do I have this backwards? Why is there something connected to me? So I guess nothing, AAA is not used in part 1. Because nothing links to AAA, but okay. Probably for part 2 it will be. Is this going to be... Okay, what's up with HHH? That's also only used... This is very suspicious. Let me finish my description, though, before we get into this. So the key AAA will be computed lazily, and it requires as input the entire rest of the map. So in order to build the value that lives at the key AAA, we need the whole map. And so, well, all right, but how are you going to build the whole map in order to pass it as an argument to the values for each of the map keys? And the trick is that's what'll happen lazily. We'll build the map, and we'll tell it what value to put at each key, but most of those will be unevaluated thunks that Haskell will evaluate as needed. One of them, well, at least one, will be an actual value. When we detect out here, we'll just say, it's 1. Or maybe we'll put a synthetic key in here named out, whose value is 1. One of those, I don't know. I guess there is no out. Yeah, it would be simpler if we just had a key in here named out, whose value is 1. And then when we say, we'll just look up, hey, what's the value for you? And Haskell will say, oh, I need to look up to okay, that's stored in the map. The key in the map at key U. The value is a thunk, which is adding together, looking up in the map BB and CC. And it'll say, oh, the thunk for BB isn't evaluated yet. I better look that up. And oh, what do you know? That's looking something up in the map named BB. Oh, and that's a thunk. It's not computed yet. Let me look up DZ, and it'll just, do it. It'll be great. Okay, so that's the plan. But what does adding AAA to this map give us that's interesting? A loop, I think, right? Because you can go from A to U to C. No. That just goes, okay. Can you get... Well, can't ever get back to A. Can we ever get back to U? No, only A does that. Okay, so I mean, this looks like an interesting node that will be used in part 2 somehow, but it doesn't do anything obviously crazy like adding a loop. Interesting. Okay. Let me make sure I understand the labeling. BVB has 2 outputs. Yeah, so these are the outputs. And we want to trace the path from the node labeled U to the number paths from node labeled U to node labeled out. Okay, great. Just check my inputs. Okay, yeah, looks good. They're all 3 letters, so I guess I'll make that required. There sure are a lot of them, huh? Okay. So what do we need first? Some types, I guess? Data... node? Sure. A node is a label for the node, and then a list. Is it non-empty? Oops. Is it a non-empty list, you think? Oh, I closed the file, the input file. Okay. Are there any of these that aren't linked to anything? That wouldn't be interesting in part 1, but in part 2, maybe it would be. No. So let's be a little bit more disciplined than maybe I am in some days. And parse let's actually require in the input that we don't have 0 children or 0 outputs. Now this node data structure is not recursive. We're not, as part of parsing the input, I just want all the lines here. I don't want to build the graph of how they're connected. We're going to do that as part of part 1. All we really need here is show, probably, right? Yeah. And type label is string. I don't think we're going to... Well, it could be a label of 3 chars if we really wanted to be responsible. Oh, boy. Sure. Why not? And what... This is, like, so pointless. Like, why do this? But I kind of like being... I don't know. So, I'm just imagining, like, it's going to be kind of annoying to parse this, right? It's not impossible. I don't know. I guess I'll just do it this way. Like, what I want to do... Here, let me write this down, and then we can just forget about it, right? I love writing types like this. Because they're parametric, right? Or polymorphic. Whatever, where it, yeah, you can have 3 of anything. There's nothing special about label, you know, about chars for labels. A label could just be a 3 of char, right? And having parametric types, you can participate in a lot more interesting type classes. Like you can fold over or map over whatever the characters of a 3, the items of a 3. Whereas label, which is fixed to just chars, there's a bunch of type classes it can't participate in. Like it can't be applicative, whereas a 3 can, right? And you can write a parser that parses like a 3 of anything is just to call 3 and then parse that thing 3 times. And then we could say, you know, new type label is a label of char or something. Or we could say type label equals whatever. This is fun to me, but I'm not going to do it today. It's just going to make everything harder for no reason. Now labels do need they need to be eq and ord and show because we're going to have them as keys of a map. Well, they don't need to be show, but we want to be able to print them so that I can confirm that we parsed the input correctly. So I think this is all we need in terms of new types for our input. So let's go ahead and write the parser, I guess. Where do I usually put... I'm going to need match sum sim. Actually, funny enough, I think I want many. And I'm going to implement sum myself to be a version that returns a non-empty. Yeah. What else do we need? Nothing, maybe? Might be it. Oh, I guess... Yeah, since we know every label is exactly 3 characters... No, you know what? I'm going to actually need to be careful. psim. I should specify that a label can't contain a new line. Right? Because otherwise it'll actually try to parse those. So psim is just a symbol matching a predicate. So we'll say it's, 3 non-new lines make up a label or whatever. Followed by a, starting with a space? Something like that. And my input is just a list of node. Actually, there's no reason data list non-empty should be part of a separate block. It's part of the prelude kind of built-in stuff. It might actually be part of containers. I don't know. Maybe I should make this part of my project skeleton and just have textregex explicative imported every day. It'd save me some typing. But I'm not going to change it for just one day. Okay, what is an input? An input is many. Many node. Each of which is followed by a new line. A node is a node of a label followed by a colon, and then some label? I think so. Now remember, sum isn't imported. We're going to have to implement this because I want a version of sum that returns a non-empty. Which is going to be completely useless because all I'm going to do is just I'm going to convert the non-empty to a list, but I don't know. It just seems nice to have data fidelity. What's a label? A label is a label containing first an ignored space and then a label char, and then another label char, and then another label char, where label stop doing that, is psim not equal new line. And sum p is p. It's the constructor for non-empty lists, f mapped over p followed by many p. Right? That looks fine. Does this compile? Missing a close quote. Data list not empty. Oh, it's not empty with a capital E, huh? Okay, this one too. This parses, great. So what? Prepare the input. The error. No parse. Oh, it's been a while since I've written a parser that didn't just work on the first try. Anything obviously wrong? Many instances of a node followed by an empty, a new line. Then, oh, I see. Our node starting, I thought, oh, I'm so clever. I'll have these 4 characters represent a node, and then like that way the spaces handle themselves. But I'm also parsing a label here, and that one doesn't start with, so I can't do that. I just have to do this here. So parse a label followed by colon, and then a bunch of labels each preceded by a space. That seems more correct. Yeah, and this parse is just fine. And we can see, for example, the last one is label XOS with just a single link to VZQ. Is that correct? Yes. Great. Oops, like that. There we go. So that's the parser. Now you just have to implement part 1. So let's import data qualify data map. I could use an int map, I guess, but like, no, that's for when the keys are ints, not the values. All right. So it's an int. I think we can just say, this is one annoying part, I suppose, of okay, you know what? U is this, out is this. This is one annoying thing of making our label type so specific, right? It's not a string anymore. All right, I got up for a second. I think I was in the middle of, I had just said I was kind of annoying that our labels weren't strings, so we have to do this, but it's fine. We have to say get is Let's see, maps, you look up once the key is the first argument. So we're going to define a map M to look up answers in. And get of a node is just look up that node in that map. And M is M insert out one, right? There's one way to get from the output to the output, I think is what we want. Yeah. And we don't have any nodes that can't get to the output, right? Because there aren't any loops and there aren't any leaves. A leaf would be a node that doesn't link to any other labels, but we looked and they all do. And I don't think there are any loops because there would be an infinite number of paths. So I think we don't have to worry about that possibility. And insert out one of M from list. Yeah, I mean, I was going to write a map here, but I guess a do is fine. And so we'll say node from twos from the list of nodes. Pure of the from, and then so what exactly is the number of paths somewhere? I think it's just the sum of all the paths of each node you can get to, right? Like if I can go straight to out, or I can go to some other node that can get to out 5 ways, then there are 6 ways I can get to out. I can go to the other node and then take one of 5 paths, or I can go straight to out and take 1. Yeah, so this is a sum. Sum map get. It's not map though, it's fmap because we're looking at a non-empty. Fmap get of 2s. Is that it? Am I done? I might be. Let's find out what the compiler thinks of this. Oh, I never mentioned the map type. That's true. Let's be clear here that we want data map lazy. Because this is a... Usually you want a strict map because you don't need laziness in the values. But here we are using the fact that the values are lazy, and we should be very explicit that we want a lazy one. Okay, name? There you go. It's a number. Is it plausible? I would have thought it would be a lot bigger. Let's run this on the test input before I submit, shall we? Well, that's the right answer for this. So I guess there aren't as many diverging paths as I would have guessed. It seems like there are a million nodes. There should be more than 400 routes, right? I guess not. Okay, 423. That's the right answer. See how easy it was? This is the whole algorithm for like sorting out the dependencies of all the nodes between each other. And most of it is just defining the start node and the end node. This, and then what it means to get in a map. Just a shorthand for getting from our specific map, I guess. Which we only use twice, but we do use it twice, so it makes sense to define it. This is the whole tree traversal, or graph traversal. We just add our base case, and then build a self-recursive map that does the computations for all the recursive cases. So, I don't know. I mean, I guess, sure. I don't need this type at the moment. So let's commit this. And indeed, we didn't use the fact that the list was non-empty at all, as I predicted. But I think it's nice to be specific about that. No, and the fact that the labels are exactly 3 characters was actually like a hindrance. It made things more annoying. But in some sense, it does make it harder to write the parser incorrectly, right? Because if I said, oh, parse 4 label characters, I got confused and wrote this. This won't compile, right? It'll say, sorry, you passed the wrong number of arguments to label, buddy. Yeah. So this is an advantage. Whereas, of course, if we made it take a string, it would accept anything. And, arguably, is that part of a reasonable part of the specification? I don't know. Maybe this should handle labels that are not 3 characters, but all of ours are 3 characters, so making the compiler enforce that is kind of nice. And we couldn't do that using the built-in string type. Anyway, on we go to part 2. Thanks in part to your analysis, the elves have figured out a little bit about the issue. They now know that the problematic data path passes through both DAC and FFT. I see. Well, this is less amenable, I think. But I think we can still use the same basic idea, right? Maybe? Like, we could store with each node 4 pieces of information. One being, how many paths are there to out, period. Another being, how many paths to out are there that pass through FFT. Another being, how many paths to out are there that pass through DAC. And the last being, how many nodes are there that pass through both FFT and DAC. And if we can get that information from all the child nodes, then we should be able to combine it into the parent node, right? It's a little bit more complicated. Would there be a better way to do this? I don't think so, but let's at least think about it before I dive into that approach. And like, there's sort of a boundary condition. Do I like have the fact that I'm in a node named FFT? I guess at that point I would be asking my child nodes, how do you get there passing through DAC? And if I'm ever at, for example, DAC, I say, how many ways are there to out through DAC? Well, all of them. All the ways to out are through DAC. How many ways are there to out through DAC and FFT? Well, it's equal to the number of ways to out through FFT. I think that idea works. So let's see. Gonna have to define DAC and FFT as labels as well and reuse them for part 2. I suppose the other thing we could do that might be much simpler now that I think about it is well, I'm not sure it's simpler. I could store 3 pieces of information at each node. One being, how many ways are there to get to DAC before passing, well, just to get to DAC period, I guess. Another being, how many ways are there to get from here to FFT? Wait, but, okay, hang on. There must be loops now, right? Because no, that's not necessarily true. And we know there aren't loops because we parsed the whole thing, and yeah, I think there aren't loops. In all of these examples, FFT is before DAC. So in this input, it's actually impossible to visit DAC before FFT, right? And in our input, maybe it's you have to go to FFT before DAC or the other way around. But you probably can't go both ways because then you could just loop forever. So one of those values, like the number of ways to get from DAC to FFT would be 0. But that's fine. So we could say, you know, the solution at the top level might be to look up from U the number of paths to FFT and then multiply that by the number of paths from FFT to out. Sorry, FFT to DAC, that eventually, and then multiply that by the number of paths from DAC to out. And add to that the number of ways you could go from U to DAC to FFT to out. One of those will probably be 0, but that's okay. So how many nodes are in my input? Oops. Oh, this is my test input. Very funny. 553. So we could compute the number of paths from... So rather than having like, oh, it stores 3 things and like having to handle each of those separately, we could just store the distance from each node to each... The number of... Not the distance. The number of paths from every node to every other node. And then at the top level, look up the 2 paths that are of interest, right? From U to DAC, multiplied by DAC to FFT, multiplied by FFT to out. Plus U to FFT, multiplied by FFT to DAC, multiplied by DAC to out. I think I like that approach. It's less... It's obviously storing a bunch of data we don't need, but, I mean, it's on the order of a few kilobytes or like maybe a meg or 2 at worst. And I think the simplicity of computing it, the kind of uniformity, will make it simpler than doing the more optimized approach. So, all right, let's lift these to the top level. You're allowed to write that, aren't you? I think so. Yes. You can give multiple... You can give type signatures to multiple things in one line and then define the things right under it. So... I guess what we want... Well... I was about to say we want a map of maps, but like... Why? Why not just have a map whose key is a pair? So... These are supposed to be multiplies. So that's the like high level definition of what nodes is. We have to define this get function, which is going to involve building a map. But I think that's okay. Where? I also always have to check. I know this is how multiplication works, but 3 times 3 plus 4 times 4. This is 25, right? Okay. I'm always the slightest bit uncertain that it's really going to parenthesize this way. But of course it does. So it's the product of these 3 things plus the product of these other 3 things. And this all type checks? Yes. Get of 2 is m lookup from 2. So now we have to build this m. M is m insert union, I guess, because, well, actually, wait a minute. Do I even have to know how many? Do I need a node for out anymore? I think so. Because the recursive case, I'm going to say, look at each child. Like, if I want to know how to get from A to B, I'm going to look at the children of A and say, hey, for each of you, how many ways can you get to B? Well, yeah. And out will never appear, but the nodes that can reach it will try to use it as a transit node. So it will need to be a fully filled in node that just has no way to any node but itself. So I guess we'll say it's union out paths and normal nodes. Out. Okay, so let's see. Insert out 1. There's one way from out to itself. And additionally, m from list of out 1 cons to do. There we go. Node from nodes, out node 0. Boy, this is so silly. This shouldn't be a do. Like this. So from out to out, there's one way. From out to anywhere else, there's no ways. For every node in the list of nodes, which doesn't include out. We should confirm this, though. Yes, out never appears. So we insert a synthetic link from out to itself and declare it dead for getting to anywhere else. And normal nodes is do. From to there's like, I guess what I want is, there's not really a better way than using lift A2, huh? Well, just have celebrate Haskell's punctuation. Everything is just punctuation. So this is the Cartesian product of nodes with itself. Get all the pairs. If from is equal to 2, we just say 1. Otherwise, it's the sum of, and now this is going to look a lot like something we did in part 1, right? Fmap get from? No. Yeah. So all the ways you could get to the current goal node from each of the children of the node. Okay, first of all, nodes isn't even... Okay. Nodes isn't a list of labels. It's actually a list of nodes. So I guess what I should be doing here is pattern matching each of them. It's just a node and then a label and then a list of children, right? Like this. Does this make any sense? I have to define a label function real quick. I guess I could just say this. There's going to be some shadowing issues now, I think, but... So map over the children a function, which is get the label of that child and then ask how many ways there are from there to my current destination and add those results. I think that makes sense. Yeah, what do you think, Haskell? You're not impressed? What do you mean data constructor not in scope? Oh, this is a typo. It should be m.bang. Oh, right. I don't actually have the children. Okay. These are just child labels. They're not child nodes. So this whole idea of needing a label was totally silly. pure of this, I guess. Surprised it doesn't want to indent. I guess that, yeah, that indent's fine, sure. M from list of do. Pure of from and then this, I guess. From to and then this. Of course, that's the actual key. Okay, now I can start actually looking at the error messages, not just glancing. What is happening here? An M map. Okay, union. What am I calling union? Yes, I have to build an entire list and then call M from list on it. It was trying to call M from list on this and then cons that onto this, which was not what I meant. Label a node, okay. Oh, true. Like that? Yeah. Right? This doesn't look good. Key is not an element in the map, huh? Okay, well, I guess I should fix this. So if we have something that isn't in the map, at least we can print what it is. What? Oh, right. If I actually want to deal with the maybiness, I can't use mbang, I have to use mlookup. So what key was missing? No way to get from FFT to out. Oh, that's true. Sort of, right? Because I didn't insert artificial nodes. I didn't insert into everything. So the map is only from keys that actually exist to keys that actually exist, except that there's a special entry for leaving out and going somewhere. There's no entry for going from somewhere to out. So let's see. I think I just want to say out const. So I'll specially insert, hey, you got to look up the value for getting 2 out from everywhere. But I can't just say nodes. I have to like say fmap label nodes. Zero. Great. Well, at least it's a number. So let's comment this out and then say, actually, I just want to see a list of all the nodes we're looking up, what values they have. Is the problem, like, which one of these is not being computed correctly, or are all of them being computed wrong? So this is crazy. There's no way to get from me to DAC. That's ridiculous. And there's also no way to get from me to FFT? What? And what's the third entry there? Zillions of ways to get from FFT to out. How many ways from FFT to DAC? Zillions. So there's something wrong with this recursive idea. Or, well, the idea is fine, the implementation's wrong. So the list of nodes does not contain out, right? We checked that already, but I'm going to check it again. Yes, does not occur. But it does contain u. That's near the beginning. Yes, it's first. There aren't, I mean, what if there were a node that were mentioned as a, but like only as a destination? This wouldn't matter because, well, I guess it would just crash. So we know that's not happening. Okay. So all the nodes are mentioned and they all have at least one child. So how many ways are there from out to out? 1. How many ways are there from out to anywhere else? 0. The get function refers to the completed map. And that get function is what is used by normal nodes. So it's not like the paths from out are missing or something is not fully computed yet. Node from and children. So our froms are all of the normal nodes, not including out. And for each of them, we get its label and its children. And then our twos are just the labels of our normal nodes plus the label out. For each pairing of those, we produce one entry in the map with the from and from then to as the key. Now 2 might very well not be in any of the children, right? It's just another node label plucked out of the air that's in the list somewhere. And we say for each child directly reachable from node, count how many ways. So maybe there's something wrong with this partial application. I don't think so, though. I want to ask for each child, how many ways can I get from that child to my actual current goal node? So if we partially apply get's second argument to be 2, we have a function that takes a node and tells you how many ways there are from that node to 2, which is my current goal. So that seems right. So what else could we try debugging? We could look at the... Well, we could try the test input, I guess. Yeah, that's maybe a good idea. What? No path from use DAC in the test input? Oh, is there a new test input for part 2? There is. I see. Did I spell one of the nodes wrong? Is that my problem? Oh, I see. I didn't notice they had changed my start point, the server rack. So SVR is a new start node that's different in some way. That it changes the graph completely. Okay. Got it. That explains why there were no paths from you to anything in my... Somewhere. You would have to scroll up to find it, but... I don't know. Maybe it's probably on the screen somewhere and I just can't see it. Oh yeah, here it is. So there were no paths from you to anywhere. That was the problem. Or to any of the relevant nodes paths, except out, which you can get to lots of ways still, of course. Okay. Let's comment this back out. Let's let's put server here because it's part of the ones that are like new to part 2. Oh, what have I done? Oh, I changed the type of part 2 as well. And this takes a while, but I think that's because we're running in GHCI. If I were to say stack run, well, it takes a while to compile, of course. Yeah, but it runs instantly, pretty much. Yeah, I mean, okay. The people writing it in Rust or whatever are doing it faster, but who cares about them? That's a lot of paths. I think it's totally plausible. I'm a little concerned that it's overflowed in int, though. No. And int is 64 bits. That's bigger than 32 bits, but nowhere close to 64, right? Let me just check. I mean, I guess that doesn't tell me whether it's overflowed, right? It could have overflowed and then still gotten to a relatively large number. Yeah, this is, you know, hundreds of thousands of times smaller-ish. It's probably fine. That's the right answer. Okay, so I had the right approach, and my implementation was right, except that I missed the key detail that we had changed the graph we were supposed to look at. We weren't supposed to look at U anymore, we were supposed to look at SVR. And so this can probably just go back to being this. And it's pretty straightforward, I think. We've built a kind of pathfinding. I mean, it's not really, because it isn't very dynamic, right? It requires n squared space, where n is the number of nodes that exist. So you couldn't use this approach for something serious, but for something small enough that you can fit it all in memory squared, sure, this just tells you the distance from every node to every other node. And then I just look up some distances and add and multiply them as appropriate. And, you know, the algorithm for computing the path from everywhere to everywhere is still pretty simple. We don't do any graph traversal ourselves. We just build a map with n times n entries, and each one of them is computed independently of all the others. Sort of, right? It refers to the answers for all of the children, but we don't have to descend into them or anything like that. We just tell Haskell, this is something I might need someday, and it makes sure to compute it all in the right order. Okay, and we didn't have any, no warnings left. Happy to commit this, all right. This part, I don't think I actually... Oh, I have fmap label of nodes, I guess, so I do need this record. That's fine. This, it would be nice maybe to... I don't know. I mean... We could write a function that takes a string and checks that it's exactly 3 characters and throws an error if it isn't, and if it is, makes it a label. And then map that over a list of strings. It would be a little bit shorter, maybe, but I don't know. Sure, and now part 1 doesn't need U and out anymore. All right, well, I'm glad that this was a much easier problem than yesterday's. Maybe it would be harder if I didn't have the magic of the Haskell runtime at my side, but I do. And I spent a large percentage of the time today explaining what we were planning to do and why it would work and how it works in Haskell, and also tracking down an error caused by misreading the problem. But actually implementing the algorithm was pretty simple for both part 1 and part 2. Hope you guys enjoyed. Thanks for watching, and I'll see you next time for day 12.